Welcome back to another lecture. It's always good to see you again, and thank you very much for following up. And it's almost midnight now, and I'm lecturing another concept here, and we're going to go through hydrogen bonding, and then also after that one, I go through through dispersion force. Okay, one way to keep you maybe awake, keep yourself awake. Drinking tea. I don't suggest this one. And like for me, it's working. I'm fine. And like I can drink, tea almost close to the bed and I will be fine. Maybe it is kind of like a Middle East, habit. I think, honestly, I think it's a Middle East habit. And like, I don't know the science behind it or whatever. But I don't encourage you to drink coffee or tea before you go to the bed. But if you want to stay awake, that's one way to do it. And I'm working from my office right now, and it's quiet, and I love it. Okay, so let's see what we have here. We were talking about hydrogen bonding last lecture, and we said in order to, technically, in order to get hydrogen bonding, we need to have two things. We need to have X, that we need to have H attached to X, and what's the X? It can be nitrogen, oxygen, or fluorine. And we need to have a Y, and Y is nitrogen, oxygen, or fluorine. And there must be a lone pair on Y. If you don't have a lone pair, there will be no hydrogen bonding, okay? Because you cannot share any electron with hydrogen. So there must be a lone pair located on one of those electronegative elements. We share it with hydrogen, okay? And also, I said hydrogen bonding is is really strong dipole technically interaction. But why do we call it hydrogen bonding? Okay, the reason for it, okay, you are not dealing with just partial negative and positive charges. Okay, you are not dealing with only like a permanent partial positive negative charges. You are dealing with a lone pair, one lone pair, and because you are dealing with two electrons sitting on a fluorine, or let's say in this case, oxygen, and you're sharing it with hydrogen, that's going to be a strong intermolecular force. So instead of having just delta minus, we have a lone pair, we're sharing it with hydrogen. And that's the reason we call it, we call it with a unique name, and we say hydrogen bonding. Okay. Now, the hydrogen bonding, okay, hydrogen bonding, again, is subject to, how much, positive or negative charges you're creating. The more hydrogen positive, the more, hydrogen bonding you have, the stronger intermolecular force you will be dealing with. Okay. And I mentioned what's the meaning of protic, versus a protic solvent or molecule is the one that has hydrogen. The one that is polar but doesn't have hydrogen, we call it a protic solvent. Okay. Now, let's keep talking about the hydrogen bonding. So the more hydrogen bonding we have, the stronger intermolecular force we will be dealing with. Okay. Boiling temperature, right? So boiling temperature straight subject to intermolecular force. Okay. So first one, because it doesn't have a hydrogen, attached to nitrogen, okay, it's not capable of creating hydrogen bonding. Yes, does have, okay, it does have like a lone pair, but there is no hydrogen. And next one, we do have lone pair on nitrogen, electronegative element, as and hydrogen as well, okay? And next one, we have all of them, but we got one more, okay? One more hydrogen, okay? So we have two hydrogen attached to nitrogen. So that means we have two places to make hydrogen bonding with two neighbor molecules. So instead of attaching just to one neighbor molecule, we can do hydrogen bonding with another one. Okay. And technically, NH2 is capable of creating three hydrogen bonding, not just also two. And let me show you what I'm talking about. So if you have nitrogen attached to CH3, for example, okay, strongest force that you will be dealing with, it will be just technically dipole. Remember, this one goes up. You cannot cancel the force. Okay, you cannot cancel the force in that case. Okay, yes. And so we say this is going to be polar, and the strongest force, it will be dipole. Okay, but what will happen if I change one of the methyl with hydrogen? Okay, if you do that one, let's say you got lone pair here. Next, I'm going to put CH3 here. Okay, let's put hydrogen here, and then CH3 there. Okay, that lone pair, it can do interaction with hydrogen that's sitting on nitrogen, and of course here you have CH3, say CH3, and a lone pair there. So this is our lone pair. Okay, and that hydrogen also, it can have interaction with a lone pair from another molecule. Okay, and say we have CH3, hydrogen, CH3. Okay, so as you see, per one, per one lone pair and one hydrogen attached to nitrogen, we managed to get interaction with two neighbors. Okay, two neighbors. So what will happen if I replace another hydrogen, another methyl group? Okay, another methyl group with hydrogen. So right now I have one hydrogen bonding. Okay, forgiven. Let's say highlight just this area. One hydrogen bonding. We're going to call this one hydrogen bonding, and the second hydrogen bonding, it will be here. So we have two of them. Okay, so we got two hydrogen bonding. Okay, let's copy paste that. Again, I'm going to change one of the methyl to hydrogen. Okay, so if I change one of methyl to hydrogen, let's say this one, we're going to change it to hydrogen. Okay, we're going to do the same thing here. Let's change that one, and for example, this one. So I put hydrogen here. Now I can have interaction with nitrogen that has a lone pair. And here we have hydrogen, and that CH3. Okay. So I managed to get the third hydrogen bonding. Okay. So technically, one nitrogen with two hydrogens and a lone pair is capable of generating three hydrogen bondings. The more hydrogen bondings you have, the higher boiling temperature you will be dealing with. So this molecule has a stronger hydrogen bonding. Okay, stronger hydrogen bonding than the one with only one hydrogen. But you have to be careful about one thing that we call it dispersion force. Okay, the molar mass of the molecule also is significant. You can't just simply ignore the molar mass. That is important. But hydrogen bonding here is playing a big role. Okay, you have two of them versus one. So hydrogen bonding is going to be the dominant factor that you need to look for it. Okay, so the boiling temperature is, when you don't have hydrogen bonding, is 3.5. You have only one hydrogen bonding. Okay, two hydrogen bonding. You get 37, boiling temperature 37. Why do I say two hydrogen bonding? One with this hydrogen. Okay, so you can reach it from this direction. Okay, through that hydrogen, or you can reach it through that lone pair. So you can actually get two hydrogen bondings. And if you replace with the second methyl group by hydrogen, the boiling temperature, it will go up to 47. Okay, but the jump is not like from 3.7 to like 37, which is like 34-degree jump here. If you look to the jump here is somewhere around, say, like, for example, 10 there and 3. So we're talking 12, okay, 12 degrees. Well, here it was technically 33.5 degrees. And why the jump is not that significant anymore? Okay, and one reason for it is like you can talk about the shape of the molecule, also and how easy actually to make hydrogen bonding or make dispersion forces. I don't really want to go really in deep now, but as you see, the jump is not that huge anymore. Okay. Hydrogen bonding, we deal with it in our daily life. And one place that I can mention, whenever, or one way actually to make cheese, you take milk, regular milk, you can buy it from Walmart, and just simply add some vinegar with it, like when it's a bit warm, add vinegar to it, and mix it, and very soon you will see, if you let it to cool a bit, you will see that technically the fat of it start to get attached to each other, and they turn to insoluble fat, and you can filter it and collect that one, and that technically is your cheese. And if you wash it, and if you will rinse it maybe a couple of times, and then put it in a mixer, and add a bit, let's say butter, and also just to get it just to turn it to kind of like a creamy cheese, you can add a bit milk to it, and that's gonna technically it will be ready to use as a spreading, like a cheese. But if you take milk by itself and you heat the milk, okay, and then you let it cool, very soon you will see a layer of fat sitting on the top of that milk. It doesn't matter how energy you spend to get it dissolve or disappear back inside the milk. That's not going to happen, because the force that, or the heat that you gave it, mess with some of the intermolecular forces. Okay. And in this case, we say we have a protein inside that milk, and that protein, it has a bunch of intermolecular forces. And in biochemistry, you read about them as a primary, secondary, tertiary, or quaternary, structure of proteins. And that heat, it will break some of intermolecular forces, and maybe the helix structure, or the sum of those interaction between the sheets, the protein sheets, will disappear. And because you lose that structure, your the compound maybe it will not be soluble anymore, and that's the reason it cannot get back inside the milk. But one very well-known disease that technically it comes from from intermolecular forces is the sickle disease, is the disease that the blood cell change shape, their shape turned to be kind of like a sickle one. And because of that, their efficiency in carrying oxygen, it will go down, and that person will suffer from kind of lack of oxygen. Okay. I want to actually start talking about that one, but before I introduce actually the disease, I want to talk about the last force that last intermolecular force that we need to cover, and that's going to be the dispersion force. Okay, and what's a dispersion force? Imagine you have a molecule. Okay, your molecule, I'm going to say CH3, CH3, CH2, CH3. Okay. So what do we have here? We have one group, okay, that is identical to that one. And this is going to be the midpoint of the molecule. Okay, so that's going to be the midpoint. So I can highlight this one, say that's a midpoint. Okay. Now, you can say, okay, the one on the right will pull to each side. Okay, so let's say we have a force here. Okay, that force is going this direction, and we're going to call it F1. Okay, we have equal force in opposite direction, and we're going to call that one F2. Okay, F1 is equal to F2. Okay, because they are 180 degrees from each other or cross of each other, they will cancel each other. So F1 plus F2 it will be equal to 0. That means mu is going to be equal to 0. So this molecule is non-polar. Non-polar. Remember, you do have a CH bond, okay? And the CH bond is a polar bond. But the molecule C3H8 is non-polar. Okay, so the molecule is nonpolar, but the molecule all the time is moving. Okay, and there is a chance that this molecule will collide with another molecule. And what will happen if you get a collision between them? So let's put it this way. We have carbon attached to another carbon, and here's the third one. Terminal hydrogen, terminal carbons, they have 3 hydrogens. And the one in the middle, it has 2 hydrogens. Okay, now I'm gonna draw this shape around it. Okay, so let's say this one is moving and collides with another molecule. Okay, so what will happen if we get collision between them? Or you know what, for temporary, like a really short time, for short time, you know, the electrons somehow they move to one side of the molecule. Okay, the electron kind of they shifted to one side of the molecule. In that case, okay, in that case, you will have a positive pole and positive poles and positive and negative poles. So either because of the collision or you know, really short time, electrons move to one side. It doesn't matter, like it doesn't matter which side. So I got this. I got an even distribution in electrons. So let's say we got negative charges here. That means the electrons happen to be on the right side. So what will happen on the left side? I'm going to have some positive charges. Okay, so here I got negative charges. There we got positive charges. Okay, can I have such a distribution inside another neighbor molecule? Yes, it can happen. Okay, and now what will happen if these 2 molecules see each other? They get close to each other. Now we will have positive charges facing to negative charges, and very soon we're going to get interaction between them. This interaction, because it's really short, okay, the time you know, time or half-life time, okay, or lifetime, okay, lifetime is really short, okay, it's really short. Okay, so because it's really short, you're not gonna get permanent positive and negative charges. So how about this? Let's call it temporary, okay? Temporary positive, negative charges. Your molecule is nonpolar, but in a short time, okay, in a short time, I got, okay, in a short time, I got positive and negative charges. So again, the lifetime is really short. It's really short. Okay. Because it's really short, you can't have those positive negative charges forever, and that means the dispersion force, or the force that you get, it will be weak. So the dispersion, the forces that we call it dispersion force. Okay. Dispersion force is different than dipole force. Okay, and why is different and why is weaker? Okay, because the lifetime. Okay, because the lifetime. So I'm going to say dispersion force will be the weakest force. Okay, it's weaker than dipole, and the reason for it is just because of the time, the lifetime for it. Lifetime is really short. While the dipole is permanent, and the strongest one, it will be the hydrogen bonding. Okay. Now, if I want to go more in depth about, you know, the dispersion forces, I'm going to say that dispersion forces are subject to size and molar mass of the compound. Okay, size and molar mass of the compound. Okay, let's you know, let's list them. Okay, so the size of molecule, and you know, size of the molecule, and also shape of the molecule will affect the dispersion. Okay, so here are some example. Okay, so we have CH3, CH2, CH3, versus CH3, CH2, CH2, and then CH3. Okay. I'm going to say dispersion force subject to size or molar mass. Okay. And so here, example that I mentioned. Okay. I have one that is the molar mass for it is going to be 36 plus 36 plus 8. That's going to be 44. So the molar mass, okay, for C3H8 around 44. Okay, molar mass for C4H10. Okay, so we have 40. Okay, we have 12 multiplied 4. That's going to be 48. 48 plus 10, 58. Around 58 gram per mole. Okay, so I'm going to say boiling temperature. Okay. So boiling temperature for C4H10 will be higher than boiling temperature of C3H8. Okay, why? Because it has higher dispersion force. Okay, it has higher dispersion force. So I'm going to say the dispersion force for butane is higher than a propane. Okay, and that's one. So as the molar mass goes up, dispersion force it will go up, and the boiling temperature it will follow it. Okay, another one. So dispersion force subject to size. Okay, size of the particle, or we can say molar mass. Okay, remember, size, okay, to the right side of periodic table increases, down in any group, forgive me. Okay. Yes, size to the right side of periodic table, size to the right of the periodic table decreases, down in any group increases. Okay, down in any group increases. Okay, so for example, we have fluorine, then we have chlorine, and that's gonna be, let's say, bromine. So I go fluorine, bromine, chlorine, and bromine. Okay, as you go down, molar mass is getting bigger. The size also will get bigger. Now, if I take two fluorine and attach them to each other, okay, yes, we will have intermolecular force. We will have, you know, a chemical bond between them. But also, we're gonna get hydrogen bond. We're gonna get dispersion force. Okay, if I just simply copy paste these two and put them close to another one. Okay, another one. So I'm going to say, if you look to this two, area that's available for, okay, for interaction between them, it will be really, really tiny one. Okay. And if I bring, you know, like, let's say, if I bring this one really close to it, okay, and zoom on it, this is going to be the one that they are in touch. In that area, they are in touch. If you compare it with chlorine, that one got bigger. Okay. Next, if you move to bromine, again, it will be bigger. Okay. So as we increase size, as we increase the size, the area or the surface that's available for interaction between two molecules goes up. So in that case, we say the dispersion force got stronger. Okay. The dispersion force got stronger. Dispersion force not only subject to the size or molar mass, okay, also is subject to the shape of the molecule. If it's linear, it's better. Okay, linear is better versus, you know, like completely spherical. Okay. Okay, so linear is better than spherical. And this is one example. Let's say we have this molecule. Okay, so I have say we have here one there, one. I think we can go with maybe 4 of them. Okay. This one is linear. And you can take this molecule and rearrange it this way. Okay, so I'm going to erase one of the hydrogen. So let's say this hydrogen is gone. Next, this piece, I will chop it. Okay. And I will attach it here. Okay. The hydrogen that I cut, I'm going to put it there. Okay. So now what happened? We got one branch. This is the main chain, and we got one branch here. Okay. Remember, the main branch used to be that one. Okay. So we're going to repeat this. Okay. I can do it a couple of times. Okay. I can, you know, like, let's say, put another one, for example, this way. So we had one here. Okay. We can cut this and transfer it there. Okay. So let's cut this one, and we're going to put it here. Okay. And this time, each hydrogen, each carbon is going to have 3 hydrogens. Okay. Now what happened? From linear geometry, we started to, you know, shifting to kind of a spherical geometry. The last one, if I draw something rounded, I can say it's almost like a spherical object. Okay, well, the first one was completely linear. So the first one was completely linear. The second one got a branch. The third one and the third one now turned to be spherical. Remember, I did not change the formula for all of them. So the formula for all, okay, for all of them, I have this formula. I'm going to write it there. I have C5 for all, and H is going to be 5 multiplied 2 plus 2, it will be 12. Okay. So the formula did not change. Because the formula did not change, the molar mass did not change. So should I get the same, you know, dispersion forces? The answer is no. Which one has the strongest dispersion force? Let's talk about it. Okay. If you have a linear, okay, linear geometry, you can get something like this. Okay. Called zigzag geometry. We have 1, 2, 3, 4, 5. Each of this represent 1 carbon. Okay. Each one represents 1 carbon. So this is a carbon that's attached to hydrogens. Okay. And what do we have here? We have 2 hydrogens. Okay. And I can say that hydrogen, technically, those, they are attached to carbon. Okay. I can put next molecule somewhere here. So I'm going to put the next one somewhere, say here. Okay. Entire of this space, it will be available for dispersion force or intermolecular interactions. So I'm going to get some interactions here. Okay. I have more area for interactions. So I'm going to say the dispersion force is up, is really high. Okay. If you start making, you know, if you branch this one, branching is going to mess with the packing. Okay? It's not going to be perfect. Okay. And if you turn it to spherical, you're not going to have much space actually, or much like technically area for intermolecular intermolecular forces or interactions. So if I put the neighbor one somewhere here and attach them, okay. So if I attach them, I have just that tiny area, okay, available there for intermolecular forces. Okay, so if you compare these two, clearly the linear geometry has higher dispersion force. So which one is going to have the highest dispersion force? I'm going to say number one. Okay, so the order for, or the trend for dispersion force will be number one, then number two, and number three is the least. Okay, so if you want to talk about boiling temperature, I'm going to say boiling temperature for number one will be higher than number two, and number three is the least. Okay, number three actually is gas. If I remember correctly, I believe is gas. Okay, if it's not gas, it's going to have really, really low boiling temperature. That means you can easily boil it. Okay. Now, intermolecular forces, we use them, okay, we use them to technically get a homogeneous mixture, or like, or we use it for the purpose of solubility. Okay, so let me go here. Let me go through the slide. So what's the miscibility? If you want to have a homogeneous mixture, okay, you need to check polarity or non-polarity of the technically the solvent or the liquid that you are dealing with. If you want to get a homogeneous mixture, you should mix polar with polar, non-polar with non-polar. Otherwise, if you mix a polar with non-polar, you will get a non-miscible, non-miscible mixture. So technically, you will get a heterogeneous mixture. Okay. And whenever we are, trying to clean, like say dirt or anything or grease from our, cloth, we use like soap. And any soap, it has two sides. One is going to be hydrophobic area. The hydrophobic area is non-polar. Okay. And there will be a head, and that head is going to be a polar side. Okay. And why do we do it? Because like most of the greases that we get, like they're coming from like meat or any like food that we eat, it has a big chain, okay, big chain of like non-polar stuff, and the solvent or the liquid that you use is water. Okay, you need to have a soap that is soluble in water. In order to make it soluble in water, we need to have that polar side. Why? Because water is soluble. Okay, water is soluble. Forgive me. Water is a polar solvent. Your soap supposed to be soluble. In order to make the soap soluble, we need to have a polar head. So that's the purpose of the polar head. Next, grease is non-polar. Grease is attached to to the fabric, your cloth. You want to pull the grease out of the fabric and dissolve it technically in water. And in order to pull the grease, we need to have a non-polar chain on the soap. Okay, and that's the purpose of it. Okay, so like as you see here, we have like a grease or whatever, and the soap is reaching it from the non-polar area and trying to technically grab the grease. Now that we have the grease, okay, so if the white one, for example, if the black one is the soap and the white one is the grease, okay, it's going to reach it from this tail, which is non-polar. Okay, they will attach it. Now the head is a polar and it will go inside water. And that way we can slowly dissociate actually the grease. And When dissociate degrees, now they turn to a smaller particle, and so the dispersion force between them, it will be less. If it's less, their solubility very soon will be, will be higher in water. Okay. Now, before I end this lecture, I want to talk about the sickle disease. And what's the sickle disease? Okay. So any hemoglobin has 4 core. Okay. So let's say this is our hemoglobin, and it has 4 core. And what do we have there? We have iron, okay, iron that attached to a bunch of nitrogens, okay, and we call them porphyrin, okay. And that's going to create technically the red cell. Okay, red cell is supposed to carry oxygen, and the way it will carry oxygen, it will be attached to this iron, and it can carry it to the cell. Now, somewhere inside the, inside this complicated protein, we have, imagine, we have something like this. So this is a piece of like, let's say, protein that is bented or peptide bented, and okay. In one area, we have this molecule. So I'm going to write structure of any amino acid. Any amino acid, you have a carbon. And one side, you have carbon attached to 2 oxygen. Okay, this one, it will be the acidic side. Other side, you will have nitrogen with 3 hydrogen. It will have a positive charge. And here we have a negative charge. And how about carbon? Okay, carbon, it has hydrogen. And there is here R. And what's the R? Okay, R, okay, it can be 1 carbon, 1 hydrogen, or other stuff. Like we have a 20 amino acid, I believe. Yeah. And how do we get the 20? We change this R or the alkyl group. Okay, you can say alkyl group. Okay, and again, the R, it keeps changing. It can be CH3. It can be just simply, like an H, or say ethyl, or other groups. Okay, now if you take, okay, if you take this, for example, here we have an amino acid. Let's say, okay, we have an amino acid, and that amino acid is this one. Okay, so we have a carbon, okay, carbon, and then carbon here. Next, we have C attached to O, and then here O. Okay, that one, let's say, okay, let's say here you have COO minus, and then I'm gonna say here that one is, you have NH3. Okay, let me touch this one there. So say this one here is attached there. Okay. Now this one is ionic, or it has a positive charge. Okay, and so in order to have like any interaction with this piece, we need to have, okay, another one is ionic here. If it's ionic, these two, they will get interacted. They will have interaction, and it will twist. Okay, and the one we have here, the one that we have in the front of it, is nonpolar. Okay, nonpolar. Okay, and because it's nonpolar, they will not interact, and the shape of the red cell, it will be almost flat, and it can easily carry oxygen. Okay, it can carry oxygen. Now, if you change this amino acid to this one, okay, so take this yellow group, get rid of that one, and the carbon that I deleted, okay, the carbon that I deleted, I'm gonna put it here. I'm gonna attach it to that one. Okay, so if I get rid of this carbon and just simply attach it to this one. Now I'm gonna get non-polar, okay, non-polar group there. Okay, that non-polar group is gonna have, okay, interaction with this one. Okay, and because of that interaction, structure of the cell, it will change and it will turn to this shape. Okay, and because we change, like technically, because the structure of the protein or the cell got changed, efficiency in carrying oxygen, it will go down. Okay, and unfortunately, like if the mutation is huge with one person, that person is going to be dealing with some complication. But you need to have like at least, like I believe, at least in three sites mutation, and then you get like, disease. Is not like if one of them happen, and then that person will be sick. But interestingly, people that they are dealing with sickle disease, they are stronger. They have strength when it comes to malaria, and I don't know what's the reason behind it, but it's a true fact, and they proved it in Africa that those people, they have more like strength against malaria. Thank you very much, and have a great time.